Okay, now the dimensions of a piece of A4 paper are measured using a ruler mark in millimeters. The results were X 110 plus minus 1 millimeter and Y 297 plus minus 1 millimeter. Calculate the maximum and minimum values of the area of the sheet of paper which these measurements give. So you have a paper right now whose values were like this. This one is giving you X equals to 210 plus minus 1 millimeter. And then this one is Y equals to 297 plus minus 1 millimeter. They're asking you to just find out the maximum minimum areas of the sheet of paper. I know area is XY. So A max is just going to be basically X max, Y max, which would actually be 211 and then 298. Okay. Just bear with me first. This one is 62,878 millimeters squared. So A min is going to be X min, Y min, which would be 209 multiplied by 296. Okay, because you have the plus minus here, right? So you just plus and minus accordingly to get the maximum minimum values. So this one is 209 times 296. You're gonna get 61,864 millimeter square. Now then I ask you, express the result of your calculation area in the form of A plus minus your epsilon uncertainty of A. Okay. Now this one here, you can actually do something like this. Your uncertainty of A can be your A max minus A min divided by 2, which is basically 62,878 minus 61,864 divided by 2. 2,878 minus 61,864 divided by 2. You're going to get it at 507 millimeters squared. So therefore, A is, if you round this to 1 SF, this one is going to be 500 millimeters squared. But you rounding up to 1 SF means you're rounding it up to the nearest 100. So your values of A, oh yeah, you did not find A just now here, right? I forgot to write this down in. 21, your area of A you need to find first. 210 times 297 goes to 62,370. Okay, this one is your area A, not the max, not the min, the normal value. So this one, you want to write down your value of A with the epsilon uncertainty will be 62,400 plus minus 500 millimeter squared. Still following the rule from before. Okay. Now, in general, to find absolute uncertainty of something, let's just say the absolute uncertainty of Y or some value, you can just find what is Y max minus Y min divided by 2. This is another way of finding absolute uncertainty other than the ones that I've written here. The ones that I've written here in the notes under pages 5 and 6, those are some of the known methods of finding absolute uncertainty. Okay. This one here, to find absolute uncertainty, where you take Y max minus Y min divided by 2 is another method to find absolute uncertainty. But this one isn't really that applicable for your paper 1 and 2. This one is actually more for paper 3 later. Okay, for your practical experiments. Okay. This one here, you won't really use it for paper 1 or paper 2. You will use it more for paper 3 later. You will know when you do your experiments once you start your school later on. This is more for when you do your paper 3 later on. To find absolute uncertainty of something, you can also use this. If you know the maximum value and you know the minimum value, you can just take the difference between them and then after that divide by 2. Okay. Now, you may be wondering, can you use whatever you learn here to find the uncertainty for this one, this case here? Yes, you can. No issues that you can actually find out. You can actually use that same method that you learn to find the answer. If let's say I say A is equals to X times Y is equals to 62,370, you know, this one will become delta A over A equals to delta X over X plus delta Y over Y. If you look at this one, look. So delta A over the area 62,370 equals to 1 over 210 plus 1 over 297 will give you your delta A as this 1 over 210 plus 1 over 297 times 62,370. You're going to get 507. Okay, therefore A is actually going to be 62,400 plus minus 500 millimeter squared. This one round to 1 SF is 500 if 1 SF. Okay, so if this one is rounded to 1 SF and it's rounded to the nearest 100, your measured value must also be rounded to the nearest 100. So you notice that your answer here is actually the same as the answer here. So both methods are applicable. Okay, you can use this one also, no issues there. Now, Tutoring oscilloscope, you may have learned this under waves, because this one under the new syllabus is grouped under waves, but previously it was grouped under measurement techniques. So I'm just going to talk a bit about this. All right, now when you want to measure when you're talking about waves, one of the things that you're interested for waves is the amplitude as well as the frequency. When we talk about waves, it is something like this. So one of the things that we normally would like to know from a wave is the amplitude as well as the frequency. So how do you actually go about in measuring the amplitude and frequency of a wave? One of the common methods that you will use is to use a cathode ray oscilloscope, or otherwise known as a CRO. Say for example, right now, you have a sound wave whose amplitude and frequency you want to determine. To be able to measure the amplitude and frequency, what you will do is that you will use a microphone connected to a CRO. Okay, you will have a microphone that is connected to a CRO. So what will happen is that you bring your microphone close to that sound wave. The microphone will capture the sound wave, and then after that, what it will do is that it will convert the sound wave into voltage signals, voltage variations. And then from there, the CRO will display the voltage as an alternating voltage waveform, like the ones that you see here, so that you can then determine the amplitude and frequency. In your notes, I think I probably wrote it as voltage and time, right? Yeah, the notes I gave to you, I probably wrote this as voltage and then time. Okay, there's some slight variations to that. It's just the terms, but it's actually still the same thing. Okay, so this one I wrote it as from which the amplitude and frequency can be determined, or you could also say from which the voltage and time can be determined. It's basically the same thing. Okay, now the waveform will be displayed as some sort of trace on your CRO screen. Now, for your CRO, there are two important settings to know: the time-based setting and the Y-gain setting. Now, the Y-gain setting actually allows your trace to move vertically, and it determines the vertical length of the trace. Okay, it allows your trace to move up and down, vertical. Okay, and it's usually expressed as volts per centimeter or volts per division. On the other hand, your time-based setting allows the trace to move horizontally, and it determines the horizontal length of your trace. This one allows your trace to move horizontally. It is usually expressed as millisecond per centimeter or milliseconds per division. Now, what is the effect of switching on and off the time-based setting and Y-gain setting on the trace that you see on your CRO screen? If I clear this off, generally speaking, if I were to switch off both time-based and Y-gain setting, if I switch off the time-based setting, my trace cannot travel horizontally. If I switch on the Y-gain setting, my trace cannot travel vertically. So it can neither move horizontally nor vertically. The only thing I'll see on the screen is just a single dot. That's all. But if then I go and switch on the time-based setting, but still switch off the Y-gain setting, now my trace can travel horizontally, but my trace cannot travel vertically. The only thing I'll see on the CRO screen is just a horizontal line. Now, if I were to inverse the setting, this time-based setting is off, but Y-gain setting is on. If time-based setting is off, the trace cannot travel horizontally. But if the Y-gain setting is on, the trace can travel vertically. So now I only see a vertical line. And then lastly, if I were to switch on both settings, the time-based and the Y-gain setting, my trace can now travel horizontally and vertically. I get to see a proper waveform of full trace like this. Okay, so this is the effect of you changing your settings. Actually, when you adjust your Y-gain setting and time-based setting, just now I mentioned that it determines the vertical length and horizontal length of your trace. It will actually affect how big the trace will look like on your screen. What I mean by that is that it will actually determine the scale of the trace. It's like when you're drawing a graph on a graph paper, you know that when you want to draw a graph, you would need to set some scale on the x-axis as well as the y-axis. Depending on the scale that you use for the x-axis and y-axis, you might actually cause your graph to look larger, or it might cause your graph to look smaller. So it's something similar here. What you're doing here, you're actually setting the scale. Okay, so that is for time-based setting and Y-gain setting. Now, then after that, one of the common things that they would like to ask you is, how do you determine your measurements from your trace? Okay, so to determine the measurements from your trace, normally you are interested in the amplitude and the frequency, right? So there's just something here. Okay, this one wasn't inside your current notes. It's just something I just added as a definition. You will have learned that period is the time taken for one complete oscillation. Frequency is the number of oscillations per unit time. And then after that, you will also have learned this in the wave section. Amplitude is actually the maximum displacement from equilibrium position. Okay, these are basically just some definition from waves. Okay, which is not inside the current version of your notes, right? The ones that you have was actually from here onwards. Okay, now to determine period T and frequency F, generally we will say this. Period is just you taking total time divided by your number of oscillations. And then frequency is just the reciprocal of the period. So when it's the reciprocal of the period and period is total time over number of oscillations, eventually you'll get number of oscillations over total time. Okay. Now in the example here, if we tell you the time-based setting is 10 milliseconds per centimeter and the Y gain setting is 5 volts per centimeter, find out the amplitude and the period. Now this one you can easily see is the equilibrium position. This is your equilibrium position. This one would be your amplitude, whereas this one would be your period. Now notice that the box here measures 1 centimeter by 1 centimeter. So you can say that the amplitude here, since it occupies 2 boxes, is 2 centimeter. Whereas the period here, since it occupies 4 boxes, is 4 centimeter. So when I want to find the amplitude now, it will be 2 centimeter multiplied by 5 volts per centimeter, giving me 10 volts. Whereas period is 4 centimeter multiplied by 10 milliseconds per centimeter, giving me 40 milliseconds. So from there, the frequency is 1 over the period. Remember to change the milliseconds to seconds. You will eventually get back the answer as 25 Hertz. So this is how you read from the CRO screen. Under some past year questions, they may ask you something slightly different, where they ask you what happens if I change the Y gain setting and time-based setting. So right now, if I tell you for the same wave, this one is for the same wave as before, as the ones that you're seeing right over here. If you increase the time-based setting to 20 milliseconds per centimeter, double that of the previous value, the period of the wave would be now 2 boxes only. What I mean by that is this. Okay. Yeah, maybe I better just clear this one off. If the time-based setting was increased to 20 milliseconds per centimeter, double of the previous value, the period is now represented by 2 boxes horizontally. You see just now the previously, this was the old setting. This one was T, and it occupied only 4 boxes or centimeter, if you would. Right now, when I increase the time-based setting, that same wave will still have the same period, but on the screen, it will be represented differently. It will now occupy only 2 boxes. Then likewise, if my Y gain setting was increased to 10 volts per centimeter, again double the previous value, the amplitude would now occupy only 1 box vertically. So previously, this one was the equilibrium. This one was the amplitude. It occupied 2 boxes. This is now the new amplitude. So this is now the amplitude. It is now only at 1 box. Okay. So if you try to make a comparison between this one and this one right now, the effect of you increasing the time base actually has the effect of squashing the graph. You see now, if I increase the time-based setting, it seems to have squashed the trace, the waveform horizontally. If I increase the Y gain setting, it seems to have squashed the waveform vertically. So you can say that increasing the time base and Y gain setting has the effect of squashing the trace seen. Okay, this one is inside your notes. But I think the last statement wasn't. From here, you can also infer that conversely, if you were to decrease the time base and Y gain setting, you will have the effect of stretching the trace seen. This one is the other relation that you can infer from. Okay, so this is CRO. Okay, this one is something you probably would have learned under waves. Okay, so this one is clear. Then the last one is micrometer screw gauge. Did you learn micrometer screw gauge in school recently?
Yeah.
Okay, right. Have you used a micrometer screw gauge before?
No.
The actual one, no. Okay. when you go for your practical experiments later on, eventually you will learn how to use this. It's actually part of your syllabus requirement, where actually when you do your experiment, sometimes they will give you a micrometer screw gauge and expect you to know how to read the values. Okay, your micrometer screw gauge looks something like this. There are actually two things that you need to know. There's actually two scales to your micrometer screw gauge. There's a main scale here, and there's a rotating scale here. What we'll do is that if say you have something like a small object whose thickness is something you want to measure, you place it in between these two ends of your micrometer screw gauge. And then what you will do is that this portion here is twistable. You can twist it. So when you twist it, what will happen is that this little end here will start to move inwards. Okay, if you twist it in one direction, it will start to move inwards. So the idea here is that you want to twist your micrometer screw gauge, the handle of your micrometer screw gauge, such that it now grips the object that you are trying to measure. Okay, you twist it until it grips the object that you're trying to measure. And then once you have ensured that it is properly gripped, then you start reading from the scales that you have here. You will have to read the main scale first before reading the rotating scale. Okay, so let's just look at some examples here. Now, if let's just say after you have properly gripped the object that you're trying to measure, this is what you see. Now, how will you go and determine the reading? You will normally just read from the main scale first, as I mentioned, before you move on to the rotating scale. What you need to do is that if you look at this one is always going to be in, the main scale here is always going to be in increments of 0.5 millimeter. So what you do is that you always look at the main scale. What is the reading just right before, what's the reading on the main scale just right before the rotating scale? This portion here represents your rotating scale. This one here is your main scale. You take the reading on the main scale that is just right before your rotating scale. If you look at this one is actually 3.5 millimeter. This one is 1.5. This one is 2. This one is 2.5, 3, 3.5. So the main scale reading is 3.5 millimeter. Then after that, what you do is you read the rotating scale. Now, when you want to read the value on your rotating scale, you need to see what is the value on the rotating scale that matches the main scale line. Okay, there's a main line here for your main scale. You see what is the rotating scale reading that matches the main line. You can see from here, this one is 31. Okay, you need to multiply with 0.01, giving you 0.31. So your reading here is 0.31. Then you add up, you get 3.81 millimeter. Okay, for your main scale, it is usually 0.5 millimeter per division. For your rotating scale, it is usually 0.01 millimeter per division. Okay, I've actually written it here. Right, this is why I have it like this here. Okay, this is generally how you read from your micrometer screw gauge. Now, there are also some cases where you will be required to interpret zero error, and then you'll be asked to correct for the zero error. Now, zero error you learned earlier on is a type of systematic error. Is where you see that your reading is not zero when it was supposed to be zero. Okay, So right now, say for example, right now, you're not measuring anything. Okay, you're not measuring anything. You twist your rotate, you twist the handle until this end here goes all the way to this other end. So that it's fully closed. When it's fully closed, you expect to see 0 here. But right now, what you see is that it doesn't really, when it's fully closed, you're not getting a purely 0 value. If it is really 0, you expect to see this. This one, I don't know whether I can draw it nicely. You will expect to see the 0 on your main scale here. And then after that, your rotating scale, you will expect to see 0 here also. The 0 here and 0 here are perfectly aligned. But right now, what you see is that when you have fully closed your micrometer, this is the 0 of the main scale, but the 0 of your rotating scale is nowhere aligned to it. It's somewhere away. This is already indication to you that there is 0 error. So if you want to find out what is the amount of 0 error here, your 0 error is actually this portion here. This one is your 0 error. What you do is you take the reading of the main scale just right before your rotating scale is actually at 0 now, and then you read the rotating scale reading that is aligned with your main scale. You can see here this one is 5, this one is 6, this one is 7, so it's 0 0.07. So you have a 0 0.07 0 error. Okay, this one is considered to be positive 0 error because you see right now you are slightly, it's very hard to see from this diagram here. You have positive 0 error because what you're actually seeing here is this is your 0, and then your rotating scale was like this. Here is your 0, and then you have your 0 0.07 here. You actually have a value that is slightly more than 0. That's why we call this positive 0 error. That's why there's a positive here. Okay, it's positive 0 error. Now, right now, if you use this same micrometer with a 0 error here and you go and try to measure the thickness of some other object, this is the new reading that you get. So if you apply what you've learned here, what is the main scale reading? It is actually 2. If this is 0, this is 0 0.5, this is 1.0, 1.5, and then this is 2. So it is 2.0 for the main scale. But then what is the rotating scale reading? This one is 30, 31, 32 times with 0 0.01, it will be 0 0.32. So your end reading is 2.32 millimeter. Now this is your current observed reading. If you want to correct for your reading, you want to correct for 0 error, you take this reading minus off your 0 error, giving you this. This would be your true measurement.
Can the 0 error be negative?
Yes, 0 error can be negative. That one is the second example that you see here. But in your syllabus, usually we're only concerned with positive 0 error. Your past year questions so far, when it concerns 0 error, it's always positive 0 error. Negative 0 error, although there is also negative 0 error, usually they don't test it. Okay, the second example that you see here is actually your negative 0 error. So we'll go through this too. Now, when you have negative 0 error, what actually happens is this. Your 0 on your main scale is somewhere here. Okay, this is the 0 on your main scale. But somehow your rotating scale actually was before this 0 here. Wait, let me just withdraw this. When you have negative 0 error, your rotating scale actually is slightly before your 0. What I mean by that is this. In your case here, let me just go with this case here. This one is now your 0 here. And then this one is some other reading here. Now, right now, if you have negative 0 error, you will notice that your main scale, your rotating scale is just before your 0 on your main scale. This is negative 0 error. If you have positive 0 error, your rotating scale is actually slightly after the 0, indicating that it's more, so it's positive. But if you have negative 0 error, your main scale, your rotating scale is actually now before your 0, okay, indicating it's actually something less. Okay, that's why we call this as negative 0 error. So what you see here is actually this one here. Okay, you can see that the 0 of the line, you can see the line for your 0 here, right? But this one here, you cannot see the line for your 0 anymore. It's already been covered by your rotating scale. It's actually something like this right now. It's actually slightly before your 0. So in cases like this, when you want to read your 0 error, your 0 error is actually read from here to here. This one you see is 1, 2, so it's 0.02. This one here in the previous example, you're also reading from 0, but you're reading it from here. Maybe I better redraw the arrow properly. For the first example, you're reading it from 0, but going to here. For the second example here, you're also reading from 0, but you're going from here to here. Okay, this one has 7 divisions, so it's 0.07. This one has 2 divisions, so it's 0.02. Now, when you first look at this, you may be tempted to just have to read it as, oh, this one is 45. So this one is 46, 47, 48. No, we don't read it like this. For this case, we read it from the 0 onwards. Okay, so we read it from the 0 all the way to the main line. It's actually 0.02 here. Our negative 0 error is actually 0.02. Now, when you go and use this one to measure something, and this is the reading that you get, you read it as normal. This one on the main scale is 2. On the rotating scale is 0.23. So it's 2 plus 0.23 giving you 2.23. Then when you want to correct for the reading, to get the actual reading, you take your observed reading minus off your 0 error. But make sure that when you minus off your 0 error, you include the negative. Once you minus off with a negative 0 error, you notice that it actually adds up. It becomes plus. This is your actual reading. Okay, so this is what we mean by negative 0 error. When you have positive 0 error, what it actually means is that when you use this, you're going to get something more than the actual value, so you have to subtract. But when you have negative 0 error, you're actually measuring something that is less than the actual value, so you have to plus back. That's why you see there's a negative and plus here. Okay, but don't worry so much about the negative 0 error. This one is not tested in your syllabus. The ones that has always been tested in your syllabus is always positive 0 error. The calculations that involve 0 error for micrometer in your case will always be positive 0 error. They actually don't really test you on negative 0 error reading. Okay, so long as you are familiar with the first example, you should be fine. Okay, right? So this one is one part. Then I move on to the last one that is on calibration curve. Okay, calibration curve is something that, okay, let's move with calibration curve. Okay, now, what is a calibration curve? A calibration curve is just simply a graph that shows you how one quantity is related to another quantity. Okay, it shows you how one quantity is related to another quantity. A lot of times, one of the axes could represent a physical quantity, and then the other axis could represent the reading of that physical quantity on the measuring instrument. Okay, what we mean by that is, say for example, if you look at the fuel gauge inside a car, if you look at the fuel gauge inside a car, when you see inside a car and then you look at the fuel gauge inside a car, there's something like a readout there with a needle. It will tell you whether your fuel is empty or full, correct? Now, the reading on your fuel gauge tells you about the volume of fuel left inside your fuel tank, okay? So what you understand is that if the volume of fuel inside your fuel tank is decreasing, your needle will go more towards this side. But if the fuel inside your fuel tank has increased, your needle will go towards the right side. Okay, basically the needle here indicates to you the amount of fuel that you have left inside your fuel tank. So it kind of relates to this, where I told you one axis could represent a physical quantity, which in this case is the volume of your fuel, and then the other axis represents the reading on your measuring instrument, which is the reading on your fuel gauge. Okay, now when you're talking about calibration curves, the one thing that we're interested to know actually is the sensitivity of the measuring instrument. Now, when we say some instrument is sensitive, it means this. If you give it a small change in input, it will result in a large change in output. It's kind of similar to the definition of sensitive for a person. For if we say a person is sensitive, you just poke him a little, then it will start to give you a very large reaction, right? So something similar here applied to a measuring instrument. When an instrument is sensitive, a small change in input results in a large change in output. So calibration curves allows you to determine the sensitivity of a measuring instrument. Okay, so right now we apply the concept of sensitivity for the example of a fuel gauge, which measures the volume of fuel inside a fuel tank. Right now, what we do is that we produce a graph which shows us the angle of deflection of the fuel gauge needle against the volume of fuel inside the fuel tank. What we have is this graph here. Okay, this one shows us the angle of deflection of our fuel gauge with respect to the volume of fuel inside the fuel tank. Your angle of deflection is something like this. Your angle theta. Okay, so right now what we want to know is that if this graph represents the angle deflection of our fuel gauge, and this one representing the volume of fuel remaining, if I want to investigate its sensitivity, is the sensitivity of the fuel gauge increasing or decreasing by looking at this graph here? Now, gradient of the graph would usually tell us the sensitivity of the measuring instrument. If I look at this graph here, the first graph here, the gradient is actually delta theta delta v. Okay, this is the gradient. Okay, delta theta delta v. Now, the delta v here, you can think of it as being your input. The angle deflection here is the output. All right. When something is sensitive, a small input gives a large output. Something similar to this one here. Okay. So right now, when I look at this one here, what can I say about the gradient? as it moves from here to here. You can see from here that if I move from here to here, my gradient magnitude is actually increasing. You can see here, let me just use a different color. Okay, I use this one. You can see here, if I move from this point to this point, my gradient is actually increasing. Now, if this one is increasing, that means this one is increasing, this one is decreasing. Now, this is similar to what you learn in maths. If y is equals to a over b, you will say that if a increase, y increase. If b decrease, y increase. Okay, this is something that you learned in maths before. Okay, if y is equals to a over b, a increase, y increase, b decrease, y would increase. Because over here we say that y is proportional to a, y is inversely proportional to b. So I want to apply the same thing here. If I see that the gradient is increasing, that will mean that delta theta is increasing, delta v is decreasing. So right now you see, for small input, I'm getting a large output. All right. So you can say that over here, because I see that the gradient is increasing, this is telling me for small changes in volume, there's a large deflection of the needle. Thus, the sensitivity is increasing. It's actually for this part here. Okay. I can say that right now, if I go from here to here, my sensitivity is increasing. Now, there are some cases also where your graph axis may be reversed, like the ones that you see here. This one is now volume over theta. The gradient of the graph would not necessarily be equals to sensitivity. It actually indicates sensitivity. Okay, you will have to interpret the cases differently. What I mean by that is that if you just look at this example here, if I were to go from here to here, notice that the gradient is also increasing. This one I say gradient is increasing, sensitivity increase. Okay. Now this one is gradient increase also. But does that mean that my sensitivity also increase? It doesn't necessarily mean the same thing. You see here, the graph shape is the same as before. Both also have increasing gradient. But just because the gradient is increasing, it doesn't mean that my sensitivity is increasing like this one here. It could go the other way around. If you look at how the gradient here is defined, the gradient here is actually delta V, delta theta. This one is my input. This one is my output. When I look at this one, the gradient is actually increasing. That would mean that this one is increasing, but then this one is decreasing. You see that I would need to have a large input for a small output. This one is actually telling me sensitivity is dropping instead. That's why this statement here, I said gradient of the graph will only indicate to you the sensitivity. It is not equal to sensitivity all the time. If you say that gradient is equal to sensitivity, it means this. Gradient increase, sensitivity increase. Gradient drop, sensitivity drop. Okay? But then if you see this case here right now, they are not telling you the same story. Gradient increase, sensitivity drop. Likewise, gradient drop, sensitivity increase. So it's not correct to say that gradient is equals to sensitivity. Instead, it's better to say gradient is a measure of the sensitivity. It indicates to you the sensitivity. You will have to interpret it case by case, like in your case here. All right, so like in your case here just now, I told you when the gradient increases as before, it now indicates that for large changes in volume, there's only small deflection of the needle. Thus, sensitivity is decreasing. This part here, is already explained by this part. Okay, so this is sensitivity. Okay, so let's just start with something simple first. Can you have a look at page 2? Now, the strain energy W of the spring is determined from the spring constant K and extension X. The spring obeys Hooke's law and the value of W is calculated using the equation shown. The spring constant is 100 plus minus 2 newtons per meter and the extension is 0.05 plus minus 0.02 meter. What's the percentage uncertainty in the calculated value of W? So this one here,
This
you
is
will
the answer B.
the answer B with this one you will know is delta W over W, and then this one is delta K over K plus 2 times of delta X over X. So you should get 2 over 100 plus 2 over 0 0.002, 0.050, then giving you, I think, some answer, right? 0.0, 0.02, 0.05 times 2 plus 2 divided by 100. Yes, the answer would be B, right? Because you got this as 0.1. This is,
Yeah, and then I times it by 100%.
yes, correct. This is fractional form. To change it to percentage form, you just need to multiply by 100, giving you 10%. Okay, so this one is okay. Right, actually for the questions that I gave you last time, did you manage to finish them all or have you tried some of them?
I think I did like half.
Okay, right. So for the half that you did, were there any problems with that?
No.
Okay, so I think maybe then we better go with the questions that you have not done to make better use of the time then. All right. Okay, so I sent you that list last time. Do you know which pages have you not done? Wait, I'm looking through my WhatsApp right now. There was some that I gave you. Specifically the structured questions. Have you tried the structured questions other than the MCQ?
Wait, let me check.
Yeah, one of the things that most students that start off with A level is this. I noticed that they all like to try MCQ first. Then after that structure, they leave it for last. Because accordingly, they say that structure takes a lot of time to do. Whereas MCQ is just one question, is easier to handle.
Yeah, correct.
Yeah. So here's the thing. MCQs, although they seem shorter and it requires somewhat a lesser attention span, they're actually more difficult than structured questions. Because what you will eventually see later on is that MCQ questions tend to test more advanced understanding of the topic. They tend to be tricky too. Like let's just say just now you mentioned, your teacher mentioned that, okay, for one particular question in kinematics, answer A, B looks fine, but then after that, the teacher said it was answer D, right? So MCQ questions, they are tricky by nature. You notice that sometimes the answer choices are very similar to each other. So the thing is that MCQs tend to test more advanced understanding. So on the other hand, structured questions, although they take longer time, they're actually somewhat better for people to start with because they test basic understanding and then they gradually build up your understanding from that. The questions are structured in such a way that they gradually build up in difficulty. They ask you to find something first, and then the next question, they'll ask you to use what you just find to find something else. So yeah, structured questions, although it seems a bit tedious to do, it's actually something that helps to build up your understanding as compared to MCQs. MCQs actually look easy to do, but actually they're not. They're actually tricky. Okay. So this is just one thing to bear in mind. Although structure seems to be a hassle to do, it actually helps better. Okay. Right. So structure questions, let me just show you first whether you're done. Have you done page 10 of the structured questions? This one.
Yeah, I was just about to say this one I couldn't do.
Okay, right. So we'll go through this one. Okay, so if you just look at this one, page 10 of the structured questions. Now you have a beam that's clamped at one end and object X is attached to the other end of the beam as shown in figure 1.1. The object X is made to oscillate vertically, and then the time period T of the oscillations is given by T equals to K square root ML cubed over E, where M is the mass of X, L is the length between clamp and X, E is the Young's modulus of the material of the beam, and K is a constant. And now after that, they tell you data in SI units for the oscillations of X are shown. Calculate E and its uncertainty. Now, when you first read this question, the first thing that you may have noticed is that you don't know what this one is. This one is actually something that you will learn in deformation of solids. It's actually one of the later chapters. It's actually a constant that is somewhat similar to spin constant, which you will learn later on. But right now, without even knowing what's the definition of what it is, you can actually still do this question. They already told you that all the values of the data is given in this table, and they're all already in SI units. Okay, they're already in SI units. So you don't need to worry so much about the units. All of them are already in SI units. You don't need to worry about needing to convert from SI to non-SI and so on and so forth. Okay, they are already all in SI units. So these are all the values here. And this one here that you see is all the percentage uncertainty. Okay. So calculate E and its actual uncertainty. So let me just write some of the stuff here. If T is equals to K square root of ML cubed over E, you want to calculate E and its uncertainty, you need to first make E the subject. Okay. So right now what you do is you make E the subject first, but before that you need to square the things. K square ML cubed over E. So E is equals to K square ML cubed over T square. Right? So far, this is what you have, correct? Now, from here, notice that this form of equation is actually kind of similar to y equals to a power m b power n, which in turn will give you fractional uncertainty of y is m times the fractional uncertainty of a plus with n times the fractional uncertainty of b. So right now you can actually say that this one is actually going to be delta E over E equals to 2 times of delta K over K plus delta M over M plus 3 times of delta L over L plus with 2 times of delta T over T. That is what you have here, right? Okay, calculate E and its actual uncertainty. So this is what you have until now. These two things are the one that are, this basically, this is the important thing that you need to have first. What's the actual expression for E? And then what's the expression that you need to get the actual uncertainty? Now, once you have this, then what you just do is you just sub in the values. Okay, you already have all the values here, so you don't really need, you already have all the values and they're already in SI units. So you don't need to bother about needing to convert from one end to another end. Okay, just assume that everything is proper already because they're all in SI units. So what you do is that you say that E is whatever the values you have here. So you have 1.48 times 10 power 5 times with, this is squared, times with 0.2068 times with 0.892 cube divided by T square 0.45 square. then you should get some value. Let me open up the partial for this. November 15 P21. Okay, so you should get the answer for this as 1.59 times 10 power 10. Okay, you should get 1.59 times 10 power 10. Then after that, all you just need to do is that you just need to sub in the values. Okay, this one way to go about this. Now your delta E over E, because all this is in percentage uncertainty form. Okay, this is all in percentage uncertainty form. You can change it to fractional form. Let me just write this. You can change it to fractional form. This one is 0.02. This one is 0.002, 0.001, 0.015. Okay, this one is in fractional form. So this one you would just say is 2 times of 0.015 plus with 0.001 plus with 3 times of 0.002 plus with 2 times of 0.02, which will in turn give you 0.77, 0.077, if I'm not mistaken, 0.077. Below 1 plus, yeah, 0.077. So your percentage uncertainty of E would be 7.7%. Actually, no need. No. That's not what I want to find. Sorry. This one, the question wants the absolute uncertainty, right? Like I said, you have actually gotten the answer in fractional uncertainty form. But the question wants it with the absolute uncertainty, delta E. So what you do is that delta E over E, you sum in the values that you have here, 1.59 times 10 power 10 equals to 0.077. So your delta E will in turn be 1.59 times 10 power 10. You get 1.22 times 10 power 9. Okay, so you have gotten up to this part, probably this one and this one. Right, so now there's another thing here. You want to express it in your proper SF form. This one, before you can proceed any further, the thing that you would notice is that you notice that this is 10 power 10, this is 10 power 9, right? It doesn't seem to match. You need to match the powers. So this one, you need to re-express it such that it's power 10. When it is re-expressed in terms of power 10, it's actually 0.122 times 10 power 10. They are basically the same values, just that this time rearranging it such that it's 10 power 10. So when you have it in terms of 10 power 10, this one and this one would now match. Now this one you see is 3SF, 3DP. You know that you need to re-express this as 1SF only. So this one will become 0.1 times 10 power 10. This one will now be 1SF, 1DP. So your measure value, as I mentioned, must follow the same DP. This one is now at 2 DP, but this one is at 1 DP. You need to round it out so that it matches the absolute uncertainty, so that it was 1 DP. So this one, I can say that, therefore, E is equals to 1.1 plus minus 0.1 times 10 power 10. This one would be the correct final answer. Yeah. Okay, sorry, not 1.1, it's 1.6, right? It's 1.59, sorry, my mistake, 1.6. This one is 1.6 plus minus 10 power 10. Okay, this is the most straightforward method that you can use right now. All right. So where was the problem with this that you have brought? What was the difficulty with this question?
I did until the the 1.22 part, and then after that I was like, how do I change it, you know?
Yeah, so the thing here is that if you see that your power of 10s don't match, you try to match them first. Because this one originally you get 10 power 9. So you need to match them together. So this one, you make it the same as 10 power 9. Then from there, you'll be able to work out already what you'll be able to work out what should be the proper expression. Okay, right? Because originally you have 10 power 9, you make it to 10 power 10. Then after that, you can see here, this is 3 SF, 3 DP. But absolute uncertainty must be at 1 SF only. So when you change it to 1 SF, it becomes 0.1, but 1 DP. Then after that, the measured value must follow the same DP. So this one originally was at 2 DP. You need to change it to 1 DP. So this is 1 SF, 1 DP. This is 1 DP. Okay, right? So that one is okay.
Okay.
Right, then have you done number 18? Page 18, sorry. This one is worth 5 marks.
No, I haven't done it yet.
Okay, right. So let me just go through it a bit with you. Okay, let's just have a look at page 18. Okay. Now you have a metal wire of length L that is cross-sectional area of diameter D. The volume V of the wire is given by V is equals to pi D square L over 4, where the diameter, length, and mass M are measured to determine the diameter, length, and mass M are measured to determine the density of the metal or the wire. The measured values are given here. Calculate the density of the metal with its absolute uncertainty. Give your answers to the appropriate number of significant figures. Okay, right. So what they want here is density. Okay, there are two ways to go about this. There's a very long-winded way and there's a very straightforward way. I'll show you both. Okay, now they told you that they want density. Density is mass over volume. All right. So right now, when you look at this equation itself, you would think, okay, the fractional uncertainty of density is equals to the fractional uncertainty of mass plus fractional uncertainty of volume. When you look at fractional uncertainty of the mass, okay, you see from here, you can easily get that value. But then the problem comes from the fractional uncertainty of the volume, because the C is not listed here. Instead, it is listed, you have to calculate it from here. So now from here, you see that.
Wait, so what question are you doing?
Page 18, am I not doing page 18?
Because it's on the same question as just now.
Oh, wait. Okay, right. Can you see the question now?
Yeah.
because I think the PDF opened a new window, so it did not follow the new window. Okay, page 18. I wait a minute. Okay, let me just reopen some of the things. Wait on. Share screen. Page 18. Okay, yeah, this is the same question as before. Right, so just to reiterate for you, there was one method that was just telling you just now. If rho is equals to m over v, then fractional uncertainty of density is equals to fractional uncertainty of m plus fractional uncertainty of v. While you may be able to find the fractional uncertainty of mass easily from the given values here, fractional uncertainty of v cannot be found directly. You have to calculate it some other way. You see that v is equals to pi d square L over 4 here. So now you may be getting the idea, okay, v is equals to pi d square L over 4. This one will in turn give you fractional uncertainty of v equals to 2 times fractional uncertainty of d plus with fractional uncertainty of L. This one you will have to ignore because they don't have uncertainties. 4 is a number, there's no uncertainty. Pi is a constant, there's also no uncertainty. So like you see now, this one, for fractional uncertainty of v, you found it here, you can now submit inside here when you say that fractional uncertainty of m, fractional uncertainty of density is equals to fractional uncertainty of v, which in turn is 2 times the fractional uncertainty of d plus fractional uncertainty of L. Now you see this method here, when you do it like this, it seems a bit long-winded, right? You just want this and you want this. This is one way to go about it, but it seems a bit messy because it's like you need to do something here, then you need to do something there before you add it up together. So there's a shortcut to do this. This one is easier if you do it like this. I'll show it on the right side here. If I tell you that density is m over v, I straight away substitute what is v inside. I will get m equals to pi d square L over 4, giving me 4m pi d square L. Now you see, once it's in this form, you can easily, maybe I don't write it here, maybe I write it at the bottom so that it becomes easier to see. So this one is now 4m pi d square L. So from here, it's easier to see that fractional uncertainty of density is fractional uncertainty of m plus with 2 times the fractional uncertainty of d plus with the fractional uncertainty of L. So this one here is actually the same as what you have here. But when you compare the two different methods, this one is much more straightforward if you have just substituted what's the value of v straight. So one of the things that people tend to do differently was this one. They tried to do this, and then they suddenly found out, oh, the fractional uncertainty of v is something that you need to find first. Then they go and find fractional uncertainty of v. Then they go and add it back up to get back the final answer. So this one seems to be a bit messy. But if you had done it this way instead, it would have made your life a whole lot easier. It's more straightforward this way. So right now, when they ask you to find the density of the metal with its absolute uncertainty, you will probably need to show this one first. This is your complete set of workings. Then after that, you proceed to find what is density. Density is 4 times of your m. You need to change to kg. 0.225 divided by 1000. Then is pi d square. D you need to change to meter. 0.38 times 10 power minus 3 square, and then your length is in centimeter. You need to change to meter, then you get this. Okay, now this one you note that you need to change everything back to SI units. Okay, so 0.3 times 10 power minus 3 square times 25 times 10 power negative 2 times with pi. You're gonna get 7.935 times 10 power 3 kg per meter cube. Okay, so this one is something that you would have. But let me just check whether I'm getting the correct numerical values for this. This one is June 16 P21. Okay, 7936. Oh, sorry. Yeah, it's correct. But I rounded it out wrongly. This one is 7.936. Okay, then after that, you would probably start to do the fractional uncertainty part. Now, the fractional uncertainty, now there's this thing I want to ask. You see, if I ask you about the fractional uncertainty of M, and then you see that this is gram, 0.01 over 0.225, would I need to change it to kg when I want to go with this this portion of the working?
For density, I
Sorry. Yeah.
think so.
Yeah, like for this one here, you see, for this part of the working, when I want to find the fractional uncertainties, you see like the case here for fractional uncertainty of the mass, this one was in grams. My question was, do I need to purposely change everything here to kg? The answer is no. You see, if I try to change everything to kg, this would mean that I need to multiply this by 10 power minus 3, multiply this by 10 power minus 3, right? Because I want to divide by 1,000. Right now, if I want to find the fractional uncertainty of the mass, and I tell you I change everything to kg, that would mean that this is times 10 power minus 3 times 10 power minus 3. Do you notice that they will actually just cancel off? So it actually is pointless to change the units because the units actually do cancel off. To put it simply, you can see it here. If it was gram and gram, the units cancel off. Even if I were to change it to kg, 10 power minus 3 kg or 10 power minus 3 kg, they will still cancel off. So when it comes to the fractional expressions, units, non-SI units do not need to be changed back to SI. Non-SI units do not need to be changed to SI. Okay? Because the units cancel off. Because the units cancel off. Right, like the ones that you see here, gram and gram cancel off. Even if you have to change to kg, they will still cancel off. It doesn't matter. So they will cancel off. But then after that, when you look back at the calculation of the density itself, like the ones that I showed here, this one you cannot leave it in non-SI units. You have to convert it back to SI units. But when it comes to the fractional expressions, you don't need to do anything about the unit conversion because you know already that they will cancel each other off. So this one, you can make your life a lot easier. You just take the values as it is. All right. That's the key take-off point that I just want you to know here. All right. So don't need to convert back the units. They will cancel. So this is plus 2, 0.01 over 0.38 plus with 0.1 over 25. This one will thus give you 225 plus this one, you give you 0.0611. Okay, then from there you want to get the absolute uncertainty, right? See, this one is you want to get the absolute uncertainty, right? This one is just fractional uncertainty form, so you need to put the values in. The bottom here may not fit. I'll just do the workings at the top here. Okay, so this one will be delta rho over 7.936 times 10 power 3 equals to 0.611. Sorry, 0.0611. So delta rho will be 7.936, giving me 485 kg meter cube. Okay, you would have probably gotten up to here. Okay, so now you have the answers like this. You would have gotten 7.936 times 10 power 3 for the value of the density. And then your absolute uncertainty, you will have gotten it as 483. Sorry, 485. So from here, how do I then proceed? You see, it's something like just now, it's a bit similar to the question just now. How do you properly express it with the correct number of significant figures? Notice that this one here is in 10 power 3. Your value of the density is in 10 power 3. What you will want to do now is that for your absolute uncertainty, you try to rewrite it such that it has 10 power 3. If you try to rewrite 485 such that it has 10 power 3, notice that it becomes 0.485 times 10 power 3. It will actually be the same value as this, just that it's now expressed differently. Now, when you have the 10 power 3 here, the expressions will now match. This is 10 power 3, this is 10 power 3. But this one, you see, it is actually at 3SF, 3dp. So you want to express it such that it has only one SF. And one SF, it will be 0.5 plus, it will be 0.5 times 10 power 3. This one is now 1 SF, 1 dp. So this one is now 1 dp, but this one, you notice it was at 3 dp. You want to round this out so that it is at 1 dp. So what you do is that delta rho, what you do is that you can just say that therefore rho is equals to 7.9 plus minus 0.5 times 10 power 3.
Wait, so I have a question.
Yep.
How did it become 0.5 times 10 to power of 3?
How did it become 0.5 times 10 power 3?
You just like make it one dp, is it?
Yeah, because you see 0.485, let me just write 0.485 is 3SF, isn't it?
Yeah.
But 3SF is 3dp, right? Correct?
Yeah.
If I want to make it to 1SF only, it should be 0.5, right?
So you always have to leave it in one SF, is it?
Yeah, absolute uncertainty must always be in 1SF. That's one of the key rules.
Okay.
Yeah, it is from this part of the notes that I mentioned. It is, yeah, page 4 of the notes that I mentioned to you. Absolute uncertainty must always be at 1SF only. Yeah, this part of your notes, page 4. Absolute uncertainty must always be at 1SF only. So like right now, I see that, yeah, it's very messy now. Let me just open something blank first. Okay, now this one might be easier to see now. So 0.485 times 10 power 3 is 3 SF, 3 dp. I round it out to 1 SF, it becomes 0.5, but at the same time, it becomes 1 dp. So now since this is now 1 dp, my measured value must also be at 1 dp, giving me this. Now this one, you will see it becomes, if I just get rid of the 10 power 3 by multiplying inside the answer, I will get the answer is 7,900 plus minus 500 kg per meter cube. This one would be the answer. Okay, 7,900 times 500. Yeah, that one is the answer. Okay. There's also another way to go through this. Let me just wipe off the ones here. I'll show you both methods. Let's write this one off. Okay, right. If just now I told, if you see that your row, I just separate out for you. This part here, you found that row is 7.9 7.936 times 10 power 3. If I put the 10 power 3 inside the expression, it will just be 7,936 kg per meter cube. Then just now this one, I found out that the density, the epsilon uncertainty of the density was 485 kg per meter cube. Okay. Now this one, I'm getting rid of the power tens. I'm just using the values as it is. Even if you had written it like this without the power tens, without the power of tens, this is the another way of interpreting your values without the power of 10. Now, without the power of 10, 7.936 times 10 power 3 will be 7,936. The absolute uncertainty that you just found is 485. You can still apply the same rule as before. This one, I can say that it is 3SF, no DP, right? But I can still round this to 1SF. This one will become 500. This one will become 500 if rounded up to 1SF. But this one, when rounded up to 1SF, still doesn't have DP. But what you do notice is that it's rounded up to the nearest 100. So when you want to write it with your density, you just round up to the nearest 100 too. So therefore, rho is 7,900 plus minus 500. Your absolute uncertainty was rounded to the nearest 100. So your value of your density, you just round to the nearest 100 too. So you notice now, between the answer that you got here and this answer that you get here, they're actually the same. Okay. So it depends on how you want to interpret it. Some people are more comfortable with working with decimal places inside the value, where some people, they are fine with no decimal places inside the value. They are fine with just rounding up to the nearest 10, 100, 1,000. So there are two different ways to go about it. It's really up to you. Okay. Right.
Okay.
Yeah, the first few examples of the structures are actually the hardest one that I can find. There's a reason why I purposely put this. When it comes to your structure questions for calculating uncertainties, the standard isn't as hard as this. Right now, what you see is that it seems to be that they just pour everything on you and expect you to work out all the steps along the way. The more recent past year questions, you will notice they are actually more guided. They will guide you step by step. For example, they may ask you to find the value of density first. Then after that, they may ask you to find the expression for the absolute uncertainty. Then the next part of the question, then they say, express the value of density with this absolute uncertainty. That one, they will structure it nicely. It's just that this question said that you have, they seem to pour everything on you at once. That's why you see this one is 5 marks. Your paper 2 is actually worth 60 marks in total. 60 points in total. Paper 1 is 40 points in total. At 5 marks, this is actually quite significant. Okay. Right, so this is one part of that. So the next structured question should be page 22. Wait a minute. 22 or 30? Okay, let's just have a look at 22. I'll clear off everything first. Calculate the density. Either 22 or 30. Wait now. The rest of it seems quite easy to do. Okay, maybe I'll go with something. Right, I'll just skip a little. There were supposed to be pages 22 and 30, but those seem to be quite easy to do. Why not we try page 44? Okay, let's have a look at page 44. Okay, have a look at page 44. And then try to do this. This is June 19 P21. This one we should be able to do it. Okay, June 19 P21. Define what is velocity. You probably would have learned it already. It is rate or change of displacement. Just try to find a way. Hey, why do you have define velocity here? June 9. Oh, sorry. June 19 P21. Page 44. Okay, define velocity. Velocity is rate of change of displacement. There's something you would have already learned in your in your kinematics chapter. So let's just quickly do this. Right, your speed v over some way through a gas or pressure P and density rho is given by the equation V is equals to square root Kp over rho, where K is a constant that has no units. An experiment is performed to determine the value of K. The data from the experiment are shown in figure 1.1 here. Use data from figure 1.1 to calculate K. So V is square root Kp over rho. You want to find K. You just sum in all the values that you have to find the value of K. Okay, so you get 1.42. This one shouldn't be an issue. Then after that, use your answer in B1 and data from figure 1.1 to determine the value of K with its absolute uncertainty to an appropriate number of significant figures. Again, all right? So without looking at the answer, now try to see whether you can get the answer and compare with the final value. You can do this, that means your basic is okay already. Okay, any problems with this?
I got 3.11 like for the change in K.
the delta K, you get one, do you get 0.17?
No, I
Any
got 3.11.
3.11? Okay, right, let's check your workings. Okay, you know that K is V square rho over P, right? That part you got that.
Yeah.
So fractional uncertainty of K would be 2 times the fractional uncertainty of the velocity plus fractional uncertainty of density plus fractional uncertainty of the pressure. Okay, now 3.11. How do you get 3. Okay, for the value of K, you got it at 1.42. That part is fine, right?
Yeah.
Okay, so if you sum in the values right now, these are all in percentage uncertainty form. I need to change it to fractional form. So did you change them to the proper fractional form? 3% would be 0.03 for velocity. 4% would be 0.04 for density. 2%.
Well, that's the problem. I didn't change it to percentage. I didn't change it from percentage.
Okay, that would be one of the reasons why. Yeah, you need to change to fractional. If you're changing it from, if you're working with fractional forms, all of them must be fractional forms. Because sometimes the marking scheme will also show you a different set of working. For your, if you look at the marking scheme, they sometimes show you the workings in terms of percentage uncertainty. I mean, like the ones that you just did, you are probably doing it like this: delta K over K times 100% equals to 2 times of delta V over V plus delta rho over rho plus delta P over P times 100%. So this one will in turn be equals to delta K over K 2 times 3 plus 4 plus 2. Wait, this one would be delta K over K times 100% equals to this. So yeah, then after that they then say that delta K over K times 100% is equals to 12%. So delta K over 1.42 is equals to 12 over 100, then giving you this. You could likewise work in terms of percentage uncertainty form. In percentage uncertainty form. Okay. Same thing as before. It depends on the individual person. Sometimes they like to work with percentage uncertainty. Sometimes they work with fractional uncertainty. For me, I prefer to work with fractional. That's why my workings looks like this. But if you look at the marking scheme workings, they tend to work in terms of percentage uncertainty. Actually, they only show you this one. But then you need to know how to interpret it to get it back to the absolute uncertainty. Okay?
Wait, so okay, so after you get the delta K is 0.17,
Okay.
then why is it that K is 1.4 plus 0.2? Like the 1.4 is from the previous one, but then how do you get the 0.2?
Oh, okay. Absolute uncertainty, the rule is 1 SF, right? This one is,
Oh, so you just, okay, yeah, never mind.
yeah, this is 2 SF, 2 dp. The rule is 1 SF. So this one will become 0.2. 1 SF, 1 dp. So measure value must be 1 dp only. That's why 1.42 at 2 dp must be rounded out to 1 dp. So therefore my answer is this. It will probably be easier if I just write this for you. This is 1 SF, 1 DP. This is 1 DP. So it's easier to see now, right? Okay. Yeah, when they have the case where they tell you appropriate number of SF, this is where you need to be careful a bit already. All right, so this one is for this. Okay, so now you notice that this one is like, basically they've started to split up the questions. First, they ask you to find K. Then they ask you to find the absolute uncertainty. If you compare with the previous question that the last two questions that you just done, they were actually asking you the same thing, but they kind of group everything together. They ask you to find the measure the final value, then they ask you to find the absolute uncertainty all within one same question. But the current one that you doing now, you notice that they've actually split up the question. They've actually split up the question already. My screen sharing is going haywire. Sorry, I need to share the screen. Where is the screen? Okay, yeah. So back to this one, you notice that they've actually split out the question. The last two questions that you did, these two would have been combined together in one single question. So that's why the difficult, it seemed difficult, but now they've actually split it up. Okay, so that part is for the uncertainties. Have you started to get the hang of it already? The questions, the format, or do you need one more just to try and see whether you're okay?
I can do it for homework and then we can like
Okay.
start something else.
All right. That one should be okay. Oh yeah. By the way, when you're doing all these questions, do you have a printed copy of it and you're actually writing on the printed copy, or are you using it on the or are you using the soft copy and writing it on the soft copy using your iPad or some other writing tablet?
Yeah, I'm using iPad.
Oh, okay. So currently, whatever you're doing right now for your past years, you're actually doing it on a soft copy form where you just write it directly on the file, is it?
Yeah.
Oh, okay. That will make things a bit simpler. Because after this, maybe I will want, since you're already practicing writing your answers in tablet form, what I'll probably do is that maybe I'll just give you some homework, and then after that, I'll just create a folder in Google Drive where maybe I ask you to write down your workings and put it inside the folder so that I can have a look through and comment on it.
Okay, can.
Yeah, okay, that one should be okay. Right, so uncertainties, you've gotten a bit of the hang of it. So let me just go through some other things other than calculating uncertainty for you. Okay, when it comes to calibration curve, did your teacher go through any questions on calibration curve for you? Let's just say, for example, I show you page 1. Do you do something like this? Page 1 of your worksheet. Anything that relates to looking at a curve on a graph and then interpreting something out of it. Did you do any questions for that in school? On page 1, you can see, right? Page 1. Have you done something like this before?
Um,
No.
I have. Wait, let me check. No, I haven't.
Okay. Calibration curve, did your teacher cover it for you? Something like what I mentioned, something about sensitivity or instrument. No, not yet.
No.
No. Okay. Right. with 10 minutes now, maybe I shouldn't go through that. I'll just go through something a bit simpler for you. Wait, let me just test you something simple first. The more difficult ones, I'll probably just leave it for your own one later. Okay, right. Page 24, 37, 57. Okay, right. Let's just have a look at page 37. Let me just see whether you know how to do micrometer reading. Page 37 of
Okay.
your worksheet. Okay, now a micrometer screw gauge is used to measure the diameter of a copper wire. The reading with the wire is in the position as shown in figure 1. The wire is removed and the jaws of the micrometer are closed. The new reading is as shown in diagram 2. What is now the diameter of the wire? When you look at this, is there zero error here? Is there any indication of zero error here from how the question describe it?
No.
There's actually zero error. You see the wire is removed and the jaws of the micrometer are closed. The new reading is shown in diagram 2, which is this one here. This one is with no object. But with no object, you notice that the zero of your rotating scale is nowhere aligned with the zero of your main scale. See, this is the zero of your main scale, but then the zero of your rotating scale is nowhere near the zero of your main scale. There's zero error here. Okay, there's actually zero error here. This one here in diagram 1 is with the object inside. So they want the diameter of the wire. They want you to find out the actual diameter of the wire. You need to correct for the zero error. Okay, so let's start with this one first. Okay, so if you want to read the reading on diagram 1, what do you think would be the reading on the main scale? For the main scale, I mentioned to you, it will be in increments of 0.5 millimeter, whereas the rotating scale,
I think it's 2 point.
okay, this one is 2 or 2.5. Okay, now let me just zoom in closer. I think this one is easier to see now. You see that there's still this line here just right before the rotating scale. So while I can say that this one is 1.0 and then this one is 2.0, there's actually 2.5 here. So this part is 2.50. This is for the main scale only. But then how about for the rotating scale? You can see that this portion here is at 9, right? It will actually be 9 times 0.01, giving me 0.09. So this one will be 0.09. This one will be 2.59 millimeter. Okay. So this one is fine.
Wait, so the second diagram, we don't have to use that at all.
This one, the second diagram, you will still need to find out the zero error. This one is with the object with zero error inside.
So they don't need you to find without the zero error.
They still need you to find without the zero error. When they ask you to find the diameter of the wire, it's understood they want the actual reading without the zero error. They want you to have corrected for the zero error. So if you put the answer as C, this one is wrong already because they want you to correct for 0 error. You get what I mean? Okay.
Yeah.
Right. So here, this one with no object, this one is the 0 error only inside. This one is with object plus with 0 error inside, but this one is with 0 error only. So now if I want to find out what is the 0 error here, this one will actually be, you see this one here is actually slightly after my 0. This one is positive 0 error. Recall that earlier just now I told you your questions will never ask you about negative 0 error. They always ask you about positive 0 error. Okay, so right now this one you have positive 0 error here. The mean scale reading just right before the rotating scale is just 0. But then what is the rotating scale reading that aligns with the main scale? You see this is 14, right? Your 0 is probably somewhere here on the rotating scale. So you read from there onwards to here, you notice that this one is 14. 14 times 0 0.01 gives you 0 0.14 millimeter. So this one, 0 0.14 millimeter is your 0 error. So now what you can say is, therefore, the actual diameter would be 2.59 minus with 0 0.14, giving you 2.45 millimeter. 2.59 minus 0 0.14, giving you 2.45 millimeter. So answer for this should be B. Okay, wait. November 18 P11 question 4, right? Answer is B. Pretty sure it is B. Okay, yeah, answer is B, right? So you need to know how to identify when you have 0 error, and then after that, from there, you correct for it. The moment you see that there's a 0 error inside or some sort of error, it's automatically understood you need to correct for it. Okay, they won't just give you a 0 error there and expect you to do nothing with it. All right, so that one is this is micrometer screw gauge reading. So this part is okay. When it comes to other micrometer screw gauge reading, there's just some there's only 2 questions in your worksheet that has it. So this is, yeah, page 57 is actually the same question. All right, so never mind, we just leave that. Okay, wait, let me just have a look at the other questions. There's some other questions that I can do for you. Okay. Maybe I try to see something for CRO for you. Okay, for CRO, do you want to do a hard question or do you want to do an easy question? There's only 1 minute or 2 left.
Easy one first.
Okay, I will do an easy one first.
Okay.
Right, so easy one would be page 4. Okay, wait. Am I looking at the correct question? CRO was written as page 4.
I think it's page 5, question 4.
Page 5, question 4. Yeah. or page 1, question 4. I really, yeah. Page 1, question 4. This one is the first question on your first page. This one is as easy as it can get. All right. Page 1, question 4. What is the time-based setting on the oscilloscope? Okay. Yeah, I need to change a bit about the wordings. Okay, page 1, question 4. You have a wave that produces sound waves of frequency 5 Hz. The waves are detected by a microphone displayed on an oscilloscope. What is the time-based setting on the oscilloscope itself? Right, so period is found by the reciprocal of the frequency, where the question now has given you the frequency as 5 Hz. This one, if you take 1 divided by 5, you're going to get 0.2 seconds. That is the period. Okay. Now, this one, you notice that your period here will be this one. This is t equals to 2 seconds. All right. But then after that, you also notice one thing in your answer. They want it in milliseconds. So 0.2 seconds, you need to change it to milliseconds first. When you want to change from second to milliseconds, milli is 10 power minus 3. So 0.2 divided by 10 power minus 3 gives you 200 milliseconds. So this one is 200 milliseconds. What you can see here is 2 divisions. 200 milliseconds for 2 divisions. You see here, this is 2 divisions. Therefore, your time-based setting is the time per division here. So a time-based setting would thus be 200 divided by 2 equals to 100 milliseconds per division. So answer is D. Okay, this is just testing you on time-based setting. Okay, right? So that should be it. Okay, so what I can do now is that later on I'll probably just give you maybe some questions. Then you try to, I'll give you some questions to do, and then I'll create a folder in Google Drive. And then what I just need you to do is probably you just write down your workings when answering the questions. Then after that, once you're done, you just put it back inside Google Drive, and then after that, I'll check from there, and then I'll write some comments there. When I'm finished with it, I'll just notify you, and you can also just check the file from the Google Drive. Can?
Yes.
Right? Because I believe my next class with you is sometime in...
It's on the 1st of November, I think.
Sometime, yeah. That one will be more than a week later. It's actually 2 weeks later. Yeah. So in that long... Yeah.
Times because wait. For me, I'm free on. Are you free on the 23rd?
23rd Saturday.
Yeah, the 23rd, like maybe
generally 23rd, yeah, fine. 23rd, yeah, I'm free. Okay, 23rd Saturday, right?
maybe like 2:30 or 3.
2:30 or 3. Yeah, fine. Saturday 2:30 to 4:30.
Okay.
Okay, so this Saturday 2:30 to 4:30. Okay, right. So that should be, so the next class I have with you is on the 23rd. Okay, 2:30 to 4:30. Right. Before that, then I'll probably just give you some questions to try, and then after that, we discuss the questions this coming Saturday. And then if we have no pending issues, then I probably will move on to kinematics for you.
Okay.
Okay. Right. And how was your waves test recently?
It was a bit hard, but I don't know.
Have your teacher hasn't given it back to you?
Not yet because there were like some students online that haven't done the test.
Oh, okay. Right. No worries. So when you get it back, just let me know a little what were the issues that you had. Then probably I can help you to sort it out when I go through waves with you. All right. Okay.
Okay.
Right. Okay. So thank you. I'll see you this coming Saturday. Have a great lunch.
You too.
Right.
Bye.
Okay. Thank you. Bye.